today's lecture, we're gonna be talking about discrete time signals, and particularly power and energy sections. First of all, we want to define and discuss how the energy of a discrete time signal. First of all, we have two types of energy in discrete time signals. The first one is a real value, and the second one is a complex value. And both of these signals are given by two different equations, which are for the real value, it's given by Ex equals the summation when n equals infinite, negative infinity to infinity, x squared of n, and x of n here refers to the input of the signal. And the second equation for the complex value is E of x exactly the same as the discrete time signal in real value. It's exactly the same, just with only one difference, as the input x of n is all squared and we take the absolute value of it. And when we compare it with the continuous time signals, we can kind of like try and see that there's a difference, that here in discrete time signals we have the summation, but instead in the continuous time signals we have the integral, and usually it's the same from negative infinity to infinity. And second, we move on to the part with the time averaging operator. The time averaging operator is a simple concept, as we use the operator to indicate the time average. If the signal x of n is periodic with period n, its time average can be contributed as with this equation. And it's exactly as the same with the power, as we will gonna see in the next slides. And when it's a non-periodic signal, the definition of time average can be generalized with like the same format, with exactly like the sign of the time average, which is that indicates like we are calculating the time average for the signal. And second, we can move on to the topic which can sum both of these equations and explain. And here in this slide, we're going to discuss the power of a discrete time signal. Power is usually a measure of the average amount of energy that a signal carries per unit of time. And mathematically, the power of a discrete time signal, x of n, can be defined as this equation right here, as this is the general equation for power when it's a real value discrete time signal, which is Px equals the time average of x squared of n. And we have two different aspects of power in discrete time signals. The first one is when it's a periodic signal, and the second one when it is a non-periodic signal. For a periodic signal, we have this equation here, which is 1 over n, the summation when n equals 0 to n equals 1, x squared of n, and this equation is used to calculate the power for a periodic signal. And we have the second equation, which is used for non-periodic signals, which is right here, which is when Px is the limit when m to infinity, with this expression right here, 1 over 2m plus 1, summation n equals minus m to m x squared of n. And something to clarify here, like that the 2m plus 1 here came from the fact that it's like the limit is from minus m minus m, so that gave us like 2m, and that's like a clarification in this equation. And yeah, that's it for like this section. Then we're gonna move into the next section, which is the power of a complex signal, which is pretty much the same as the real value signal, but we have a different thing only, which is the absolute value. And this is the only difference between between like the complex signal and the real value signal. It's exactly the same, but with the fact that we have to use the absolute value of the input signal, x of n, to get the power of the signal. When even it's a periodic and non-periodic, it's exactly the same. And then we can have a discussion about like the energy signals versus the power signals. And usually in this section we can see that there is a key difference between power and energy, and that can be expressed as that power can be finite or infinite, while energy is always finite. And we can also say if a signal has a finite energy, it must also have a finite power. However, a signal with an infinite energy can still have a finite power as long as like the power per unit time remains within certain boundaries and remains bounded. And also we can add to this one more important difference in this topic, which is the power is useful for analyzing signals that are periodic or have a repetitive pattern, while energy is useful for analyzing non-periodic signals or signals with finite duration. And we can say this is because the energy of a periodic signal is infinite, while on the other hand, the power is finite. And then lastly, we can discuss how this like the power and energy are different in continuous time and discrete time. And the main difference between power and energy in continuous time and discrete time signals is the way that the signals are measured. Like in continuous time, we can see that power and energy are measured over an infinite period of time, while in discrete time they are measured over a finite number of samples. As a result of this, the definition of power and energy are slightly different, and here we can see a graph that kind of like expresses how the continuous and discrete time signals are different. And we can say also within this graph, we can also conclude that another key difference is that continuous time signals can have infinite energy, while discrete time signals can have finite energy. And this is because the key difference between both, which is the integral and the summation. For discrete time signals, we use summation, but for continuous time signals, we used to calculate power and energy using the integral. And that's the main differences between the continuous and discrete time signals. Hello everyone, in this video we're going to be discussing discrete time power signals, an example and help demonstrate the idea of how to use the equations we get to know in the lecture video in order to calculate the power of a signal. First of all, we have this graph of a signal, and as we can see, it looks like it's periodic from like this point to this point. We can see how repetitive it gets, and we can determine from this that it's a periodic signal. And then we can start solving this equation, this problem, and we're gonna be starting with setting the equation of P power 1 over n, the summation of n equals n absolute value of x of n squared. Then we're going to be substituting with our values, as we're going to get the n as 4, and as you can see from here, we have the n we can determine by from here, as this is -1 and 0 and 1 and 2, and those in total are 4, and that's the period we're having. So the n equals 4. Then it's summation of the two limits when n equals -1 from here to when n equals 2 till here, one and getting the absolute value of x of n squared. Then we can be simply substituting our x of n values in this equation and start getting the results for p. And from here we can say we got 2. We're going to substitute every value of x of n, which is 1, which is 2 squared, and 1 squared, and then the other two values will be 0. And as you can see here, we can see that this one, the x of n value is 0, and this one, the x of n value is 0. Here it's 1, as you can see here, and here it's 2, and that's how we got these values. And then we're gonna go and calculate p, as we're gonna get p equals 5/4 watts, and that would be our final answer for this example. And as we can see from this answer, we can tell that p is finite from here. This is finite answer, and that's why we can say x of n of the signal is a power signal indeed. And yes, that's everything for this example video, and I hope that kind of gave you an idea on how to solve any problem with a step-by-step guide as on how to use the equation and analyze the graph and substitute your values. Are we gonna get the result at the end? In this lecture slide, we'll be solving an example on discrete time energy signals. We got this example right here, which is x of n equals 1/3n u of n, and we are asked to calculate the total energy. First of all, we can start solving this example by stating the energy equation, which is this equation x of n squared. Then we substitute in order to start solving the equation. And we set the limits from -infinity to +infinity. And here we have the input of 1/3 and u of n all squared. And when simplifying this, we're gonna get +infinity and n equals 0, 1/3, and the u of n will be cancelled. This is to the power of 2. Then furthermore, we'll have the square here applied, as this is gonna result with the following equation, which can be expressed as like this. And then we can determine the result of this equation as E equals 1 plus 1/9 plus 1 over 9 squared, and we can continue in this sequence 1 over 9 cubed and so on. And as we can see from this, uh, we can get the equation as we can see this type of sequence. We can see that we can put the total energy as when it's to infinity, it's equal to A1 over 1 minus R, and 1 minus R in this equation, it refers to the 1 over n, 1 over 9 right here, and A1 is the 1 right here. And this only applies when the value of R is less than or equal to, is like between -1 and 1. And yeah, we can go on and simplify with this to get the result of 1 over 9, and this will equal at the end 1 over, or I'm sorry, 9 over 8 joules. And yeah, I hope this example helps a little bit to improve our understanding to the energy problems and how we can use the equations given to solve any problem.